Welcome to the fifth session of this circular function series. In this session, we will demonstrate how to apply compound angle formula to simplify trigonometry expression and solve trigonometry function using general solution form approach. In addition, we also demonstrate how to use angle addition formula to solve inverse trigonometry function related problems through 10 worked examples.
Hello, Math Champions! I'm Dr. Chen. If you want to improve your math skills and understanding so that you gain confidence, enjoy math more, and get better results, click subscribe and hit the notification button so that you don't miss anything.
Welcome to the fifth session of the circular function series. Here, example 1 is to evaluate a trigonometry expression with sine and cosine functions, given that tangent alpha equals square root 3. Since we know tangent alpha equals square root 3, we need to transform all the functions to tangent function. So here both the numerator and denominator are divided by cosine squared alpha. So the original expression becomes the ratio of 4 minus tangent alpha minus tangent squared alpha, or to the result of 2 tangent squared alpha plus tangent alpha minus 5. Then we substitute tangent alpha by square root 3 and then obtain the value of the expression, which equals square root 3 minus 2 after being simplified. In example 2, angle A is an angle in triangle ABC, and sine 2A equals 2 over 3. The question is to evaluate the sum of sine A and cosine A. Since sine 2A equals 2 over 3, which is greater than 0, therefore A is an acute angle. Then we expand the expression of sine A plus cosine A, or in parentheses squared, which equals 1 plus sine 2A, which equals 1 plus 2 over 3 equals 5 over 3. Hence, sine A plus cosine A equals square root 15 over 3. Example 3 is to evaluate cosine pi over 2 plus alpha, given that cosine alpha equals 1 over 5 and alpha is in the fourth quadrant. According to the complementary relation between sine and cosine functions, cosine pi over 2 plus alpha equals negative sine alpha, which equals square root of 1 minus cosine squared alpha, which equals 2 square root 6 over 5. Hence, cosine pi over 2 plus alpha equals 2 square root 6 over 5. Example 4 is to evaluate a trigonometry expression with cosine, tangent, cotangent, and cosecant functions. The first step of evaluation is to simplify the expression according to the relations of 1 plus tangent squared alpha equals secant squared alpha. Cosecant squared alpha minus 1 equals cotangent squared alpha. Hence, the expression becomes 1 over the product of cosine alpha and the modulus of secant alpha plus the ratio of 2 cotangent alpha to the modulus of cotangent alpha, which can be further simplified to secant alpha times the modulus of secant alpha plus 2 times the modulus of tangent alpha times cotangent alpha. At this point, we need to discuss the location of the angle alpha. When alpha is in the first quadrant, the trigonometry expression equals 1 plus 2, which is 3. When alpha is in the second quadrant, the expression equals negative 1 minus 2, which is negative 3. When alpha is in the third quadrant, the expression equals negative 1 plus 2, which is 1. Finally, when alpha is in the fourth quadrant, the trigonometry expression equals 1 minus 2, which is negative 1. In conclusion, the original expression equals 3, negative 3, 1, or negative 1. Depends on which quadrant the angle alpha falls into. Example 5 is to find which quadrants the angle theta will fall into that satisfying the trigonometry inequality of half to the power of sine 2 theta is less than 1. Since the right hand side of the inequality 1 can be written to half raised to the power of 0, sine 2 theta then is greater than 0. As we know, sine function is greater than 0 when its angle is in the first or second quadrant. Hence, theta is between n pi and n pi plus pi over 2, where n is an integer. Now, in order to find which quadrant the angle theta falls into, we need to discuss the parity of n. When n equals 2k, which means n is an even number, theta is between 2k pi and 2k pi plus pi over 2, which means it is in the first quadrant. When n equals 2k plus 1, here n is an odd number, theta is between 2k pi plus pi and 2k pi plus 3 pi over 2, which is in the third quadrant. In summary, angle theta falls into the first and the third quadrant, that satisfying the inequality. Example 6 is to evaluate a trigonometry expression of tangent squared alpha minus cotangent squared alpha, given that tangent alpha plus cotangent alpha equals 10. Since tangent alpha plus cotangent alpha equals 10, we have the quadratic-like trigonometry equation of tangent squared alpha minus 10 times tangent alpha plus 1 equals 0. Now let's come back to the expression we are going to evaluate. Since tangent squared alpha minus cotangent squared alpha is factorized to tangent alpha plus cotangent alpha, or in parentheses times tangent alpha minus cotangent alpha, or in parentheses, which equals 10 times tangent alpha minus its reciprocal, or in parentheses. Since we have the quadratic-like trigonometry equation, we may use the quadratic formula method to find the value of tangent alpha, which equals 5 plus or minus 2 square root 6. Hence, we may calculate the value of tangent squared alpha minus cotangent squared alpha, which is now expressed to 10 times tangent alpha minus its reciprocal, or in parentheses. So when tangent alpha equals 5 plus 2 square root 6, the original expression equals 40 square root 6 after being simplified. When tangent alpha equals 5 minus 2 square root 6, the original expression equals negative 40 square root 6. In summary, the value of tangent squared alpha minus cotangent squared alpha equals plus or minus 40 square root 6. Here we continue to work on an alternative approach to solve the problem in example 6. Since tangent alpha plus cotangent alpha equals 10, tangent squared alpha minus cotangent squared alpha equals 10 times tangent alpha minus its reciprocal, or in parentheses. Since tangent alpha plus cotangent alpha, or in parentheses squared, equals tangent squared alpha plus 2 plus the reciprocal of tangent squared alpha, which equals 100. Tangent squared alpha plus its reciprocal equals 98. However, tangent alpha minus its reciprocal or in parentheses squared equals tangent squared alpha minus 2 plus the reciprocal of tangent squared alpha, which equals 96. Hence, tangent alpha minus its reciprocal equals plus or minus 4 square root 6. Accordingly, tangent squared alpha minus cotangent squared alpha equals plus or minus 40 square root 6. Example 7 is to evaluate the trigonometry expression tangent theta plus tangent pi over 2 minus theta, given that sine theta plus cosine theta equals square root 2 over 3. Since it equals square root 2 over 3, sine theta plus cosine theta, or in parentheses squared, equals 1 plus 2 times sine theta cosine theta, which equals 2 over 9. Hence, sine theta times cosine theta equals negative 7 over 18. Now, let's look at the expression we are going to evaluate. Tangent theta plus tangent pi over 2 minus theta can be written to tangent theta plus its reciprocal, which can be written to 1 over sine theta cosine theta. So, tangent theta plus tangent pi over 2 minus theta equals negative 18 over 7. Example 8 is to solve an trigonometry equation square root 3 cosine x minus sine 2x equals 0, given that the domain is between 0 and 180 degrees. The first step is to use the double angle formula and then factorize the equation by taking out the common factor cosine x. Hence, the equation becomes cosine x times square root 3 minus 2 sine x, or in parentheses equals 0. Then we apply the null factor law to find all the x values that satisfy the equation. So x equals pi over 2 when cosine x equals 0. When square root 3 minus 2 sine x equals 0, x equals n pi plus negative 1, or in parentheses to the nth power times pi over 3. Based on that, x equals pi over 3 when n is 0. X equals 2 pi over 3 when n is 1. In conclusion, x equals pi over 3, 2 pi over 3, or pi over 2. The criteria in example 9 is that P equals cosine A plus sine A, Q equals cosine A minus sine A, and the angle A is measured in degrees. There are two questions in this example, and the first one is to evaluate P squared plus Q squared. The second question is to prove the relation of P over Q equals tangent 45 degrees plus A. Since P equals cosine A plus sine A and Q equals cosine A minus sine A, so P squared plus Q squared equals cosine A plus sine A, or in parentheses squared, plus cosine A minus sine A, or in parentheses squared. After the two complete squares being expanded, P squared plus Q squared equals 2. As for the second question, P over Q equals the ratio of cosine A plus sine A, or to the result of cosine A minus sine A, which can be further simplified to the ratio of tangent 45 degrees plus tangent A, or to the result of 1 minus tangent 45 degrees times tangent A. As it can be seen, this is the addition formula of tangent function. Therefore, P over Q equals tangent 45 degrees plus A. Example 10 is to find the domain and period of the given circular function. In order to find the domain and period of the function, We need to simplify it first, and there are two approaches to simplify this given circular function. As for the first approach, the initial step is to multiply a number square root 2 over 2 on both numerator and denominator. Since square root 2 over 2 can be written to sine pi over 4 or cosine pi over 4, then every term in both numerator and denominator can be transformed by applying the product to sum formula, as shown in red here. Hence, after further simplifying both numerator and the denominator by collecting or cancelling like terms, the expression equals the ratio of cosine 3x plus pi over 2 to cosine 3x. As we are familiar that cosine 3x plus pi over 2 equals negative sine 3x. The function becomes negative tangent 3x. So the domain of the function is all the real number except n pi over 3 plus pi over 6, where n is an integer. Hence, accordingly, the period of the function is pi over 3. Here we continue to work on the alternative approach of example 10. With this approach, instead of multiplying square root 2 over 2 on both numerator and denominator, we directly expand cosine 3x plus pi over 4 and sine 3x plus pi over 4 using addition angle formula, as shown in red here. After collecting and cancelling like terms in both numerator and denominator, the function can be simplified to the ratio of negative square root 2 sine 3x to square root 2 cosine 3x, which equals negative tangent 3x. After the function being simplified, both domain and period can be found. Hence, the domain of the function is the real number except n pi over 3 plus pi over 6, where n is an integer. Accordingly, the period of the function is pi over 3. If you enjoyed this video, please give it a thumbs up and subscribe to help me make more math content like this. I will see you in the next video.